Hi everybody. Let's walk through the solution to the last of the extra credit problems, which I said was maybe the trickiest one. You're finding the nth derivative of the function x to the n over 1 minus x, where n is a natural number, so n is an integer that's 1 or greater. Alright, so I'm going to walk you through kind of the thinking process that I would use if I were a student sort of approaching this for the first time. So the most obvious thing to try is let's just try and take the derivative a bunch of times and see if there's a pattern. So if I'm taking the derivative here, I'll probably be using the quotient rule. And as you take more and more derivatives, you're going to see that it just gets messier and messier and messier. So if you did that on the test, that is a very natural thing to start out doing. But at a certain point, you would probably want to stop and back up and think, well, if I'm getting really messy derivatives, maybe there's a clever algebraic simplification that I could use earlier on, which would simplify the problem. So something that I think of a lot when I'm stuck on a problem is I think, what's the piece of this problem that's making it difficult? Or what's the piece that's making it ugly? So when I was taking derivatives, the thing that was making it ugly was the fact that it was the quotient rule. So I thought, wouldn't it be nice if there was some simplification we could do that would let us simplify away this 1 minus x? So I was sort of brainstorming, what could I do to simplify away? And I remembered way back at the beginning of the unit, we had that proof of the power rule where we used this particular algebraic trick. Remember we had, well, let's do it with a specific example first and then we'll generalize. If you have like a cubed minus b cubed, for example, we decided you could rewrite that as a minus b to the a squared plus ab squared plus, to the ab plus b squared, like this. And in general, if you have a to the n minus b to the n, you could rewrite that as a minus b, and then here you'd have a to the n minus 1 plus a to the n minus 2b, and so on, until at the other end you would have a b to the n minus 1 plus b to the n minus 2 plus b to the n minus 1. So we had that simplification that we used to allow us to do a very similar cancellation in the proof of the power rule. So this occurred to me because I thought, okay, well, I've got something to the n, and that's almost fitting this pattern, and I know that I've used something like this before to do a cancellation in a kind of a similar circumstance. So I thought, I wonder if I could manipulate this so that way I could use this type of simplification and then cancel what I want. So here was my thought. I thought, let's rewrite this so that we've got x to the n minus 1 plus 1. And the reason, so first of all, observe that I haven't actually changed the value of anything here. I've added a special form of 0 because these would cancel out. But what this lets me do is, this lets me rewrite my x to the n as the difference of nth powers, because 1 is really the same thing as 1 to the n. So now that I've done that, I can sort of think about this in two parts. I've got my x to the n minus 1 to the n, and then separately over here I've got my plus 1. So this will let me split it into kind of two separate problems. I've got my x to the n minus 1 to the n, and then I've got my 1 over 1 minus x. Okay, so this hasn't obviously helped yet. This will only help if after applying the simplification, this will really let us simplify this away in a convenient way. So let's check and see. So here I'm going to rewrite this as x minus 1 times x to the n minus 1 plus x to the n minus 2 times 1 plus x to the n minus 3 times 1 squared is just 1, and so on, until eventually I get down to x times 1 to the n minus 2, and then plus 1 to the n minus 1. All right, so I've applied my simplification, and that's all over 1 minus x, and then don't forget I've still got this part over here, which is 1 over 1 minus x. Okay, so how has this helped me? Well, if I factor out a -1 from here, that's going to give me, here I've got a 1 and a minus x, and here I've got a 1 and a minus x. So now, just like I was hoping, this is canceled. And now I've got this. Oops, yikes. Okay, so now I've got it looking like this. And remember, I haven't taken any derivatives yet. This is still, I'm just rewriting my function, and I'm hoping to get it into a form where when I take the derivatives, they'll come out simpler. So this is nice because I could distribute the negative in here. And now I've got a situation where, yes, I have a lot more terms to deal with, but each of the terms, when I take derivatives repeatedly, is just the power rule repeatedly. So that's really nice. Well, at least that's true for these ones. For this term, you might be looking at this thinking, oh, well, you haven't really helped. You're still using the quotient rule. But remember, I can rewrite this as 1 minus x to the -1. So here I can still use the power rule followed by the chain rule. So this is feeling like it's going to come out more simply when I take derivative. So now it's time to remember another fact. We had a homework problem at one point where I asked you, I forget exactly what I asked you, but it was something like this. Like, let's imagine taking the 5th derivative of x to the 5th, and then imagine taking the 6th derivative of x to the 5th. So, here, let me readjust here. So if I take the 5th derivative of x to the 5th, let's see what happens. So the first derivative is going to be 5x to the 4th. Then the second derivative, using the power rule, the 4 will come down, so I'll have 5 times 4, x cubed. Then the third derivative, the 3 comes down, so 5, 4, 3, x squared. Then for the fourth derivative, the 2 comes down, so 5, 4, 3, 2 times x to the first power. And so then for the fifth derivative, the 1 comes down, so I've got 5, 4, 3, 2, 1, and then x to the 0 is just 1. So when I take the fifth derivative of x to the fifth, I end up with 5 factorial, which is just a constant. So if I were to take another derivative, the derivative of a constant, of course, is just 0. So if I take the sixth derivative of a fifth power polynomial, I'm going to get 0, because as you take derivatives, the powers go down until eventually you have a constant, and then the derivative of a constant is 0. So in general, if I have x to the n, and I take the nth derivative is going to be equal to n factorial, but any larger derivatives than that are going to be 0. So let's see how that fact applies here. Remember, the original question was asking for the nth derivative of this function. So let's look at all my terms here. All of my terms here are powers that are smaller than n. So if I take n derivatives of just that term, the n minus 1 is going to come down, and then the n minus 2 is going to come down, and eventually I'll end up with n minus 1 factorial, and then I'll take another derivative, and it'll become 0. So actually, when I take n derivatives, this term goes to 0, that term goes to 0, all these terms go to 0. So all I really need to do to solve the problem is think about, what is this going to become when I take n derivatives? So let's think about that. What did I have? I had 1 minus x to the -1. Okay, so this is a situation that's simple enough that you really can take repeated derivatives and spot the pattern. So my first derivative, the negative will come down, and then this becomes -2. But remember, there's an inner function, so the chain rule says I have to multiply by the derivative of that inside. The derivative of this is -1. So that'll become positive. Okay, second derivative. The -2 will come down. This becomes -3. But again, because of the chain rule, I multiply by a -1, and that becomes positive. So for the third derivative, I hope you're spotting a pattern here. The -3 comes down. And this is -4. Chain rule, that becomes positive. So it looks like I'm ready to jump to the nth derivative. When I had the second derivative, it was 2 factorial for a coefficient. The third derivative has 3 factorial for a coefficient. So the nth derivative, I'm expecting to have n factorial as a coefficient. And then the exponent here should be negative n plus 1, because it's going to be 1 larger than whatever derivative I have. Well, the magnitude is going to be 1 larger. And that's it. So that's the answer to the problem, because due to the simplification that we made here, all of those other terms, the nth derivative is going to end up being 0. So is this the only way to solve this problem? Definitely not, but I was hoping to lead you through how somebody might think about it from the point of kind of not knowing what to do and trying to connect it to situations that seem similar that you've dealt with in the past. Because all of these simplification moves that I made that might have seemed like, how would anybody ever have thought of that? I hope it doesn't seem like magic, because really it just comes from, first, desperation, and then second, remembering past problems and being able to spot things that don't look exactly the same, but that are similar enough that you could force your thing into the form in which they'd apply. So x to the n is similar enough to a to the n minus b to the n that it let me introduce something that would let me force it into the appropriate form to solve.